Okay, let's unpack this fascinating, brilliant, and, well, profoundly complex figure. Erwin Rudolph Joseph Alexander Schrödinger.
It's a name everyone sort of knows.
Right. We know the name because of two things: a mind-bending equation and a very famous, potentially deceased feline.
Exactly. But the genius behind those concepts was anything but simple. For the general public, Schrödinger is either the man who defined modern quantum mechanics or he's the guy who came up with the idea of a half-dead cat stuck in a box.
And our mission today is to go far deeper. We're going to dive into the sources to understand the theoretical physicist, the philosopher, the political exile, and, critically, the deeply complicated and controversial man that his history reveals.
Yeah, there's a lot to unpack. We're talking about an Austrian-Irish theoretical physicist. He shared the 1933 Nobel Prize in Physics with Paul Dirac.
And the sheer scope of his intellectual output is just staggering. I mean, he didn't just invent wave mechanics. He inspired biology, wrestled with the nature of consciousness, and defined an entirely new vocabulary for how we discuss subatomic reality.
That's the core of the challenge when studying him. You have to balance these monumental, world-changing scientific contributions, which really center on the Schrödinger equation.
The fundamental description of how a quantum system evolves dynamically in time.
Right. You balance that with the philosophical legacy,
Mm.
which is mostly defined by Schrödinger's cat.
Which, as we'll see, is so often misunderstood.
It really is. That thought experiment was actually a profound act of rebellion against the very theory his equation made possible. This tension between creation and rejection is, I think, the narrative thread we'll be following today.
So let's establish the context for his entire life. It seems like his nonconformity was rooted in a pretty diverse background.
It really was. Schrödinger was born in Vienna in 1887, and his personal history starts with this blended heritage, which I think provided the foundation for his later, very wide-ranging intellectual interests.
He wasn't a standard, uniform upbringing then.
Not at all. His father, Rudolf Schrödinger, was a dedicated botanist and a Catholic. His mother, Georgine Bauer, was Lutheran. And to top it off, her father was a chemistry professor at TU Wien.
So you have this blend of disciplines right there in the house from the very beginning: science and philosophy, botany and chemistry.
It's all there. And it wasn't just the mix of disciplines, but the cultural mix, too. The sources point out a key advantage he had from a very young age, one that really facilitated his future international career.
Let me guess, language.
You got it. He was an only child, and his maternal grandmother was British. So because of that, he learned English outside of any formal schooling.
And that fluency would have been invaluable. It allowed him to engage with the global scientific community and later, to move across countries with relative ease.
Especially when political necessity forced him to. It was a huge advantage.
So he spent his foundational years at the University of Vienna from 1906 to 1910. He studied under some pretty influential figures.
Oh, absolutely. People like Frances Exner, and his doctoral advisor was Friedrich Hasnerl, who was himself a student of the renowned physicist Ludwig Boltzmann.
That's an incredible intellectual lineage right there.
It is, and it anchors him firmly in the tradition of classical deterministic physics, particularly statistical mechanics, which was Boltzmann's specialty. This is a really critical detail.
Why so critical?
Because he wasn't trained in the revolutionary quantum ideas that were just starting to bubble up. He was trained in the mechanics of the previous century. And that, I think, explains why he spent the first decade of his career not as a theorist, but as a practical, rigorous experimentalist.
That's the detail that really surprised me in the source material. We think of him purely as this mind that dealt in abstract equations.
I know, right? But before 1919, he was hands-on, collaborating heavily with Exner.
So what kind of experiments was he doing?
It's a crucial insight into his intellectual evolution. We see him exploring applied fields that required immense empirical rigor. Things like electrical engineering, atmospheric electricity, and atmospheric radioactivity. This background means his theories weren't just mathematical constructs, they were rooted in physical observation.
And his early research wasn't just, busy work. He was successful. The sources point to some specific highlights.
A great example comes from 1912. He wrote a detailed article on something called dielectrism, basically the study of electrical insulators and how they react to electric fields.
Okay, pretty technical stuff.
Very. Then, in 1913, he moved into atmospheric studies. He produced a theoretical estimate of the height distribution of radioactive substances. He calculated how much radon and thoron should be present at various altitudes to explain the radioactivity they were observing in the atmosphere.
So that sounds like a highly specific, measurable prediction.
Exactly. And the sources confirm this wasn't just hypothetical. Experiments that were later carried out in a place called Z-Ham confirmed his theoretical estimate.
And that work got him some recognition.
A lot of recognition. It was so significant that it earned him the prestigious Heininger Prize of the Austrian Academy of Sciences in 1920. His final physical experiment before he fully shifted gears was on coherent light in 1919. So by the time he became a full-time theorist, he had established credibility in multiple experimental domains.
That progression from foundational classical training through practical experimental success to eventual abstract theory, it really makes his later resistance to the probabilistic quantum interpretation seem less like intellectual stubbornness.
And more like a deeply felt commitment to a deterministic reality.
Yes.
It absolutely frames his philosophical resistance.
But that academic progression was, like for so many others, abruptly put on hold.
Global conflict. He served throughout the Great War as a commissioned officer in the Austrian fortress artillery from 1914 to 1918. He was stationed in strategically important areas like Gorizia and Duino.
Serving in the artillery is such a stark contrast to his scholarly work, and once the war was over, his career just took off with extraordinary speed. It suggests institutions were desperate to bring minds like his back into academia.
It was dizzying acceleration.
Yeah.
I mean, in just 2 years, from 1920 to 1921, he held 4 different positions. Four. He was an assistant to Max Wien at Jena, then an associate professor at Stuttgart, rapidly followed by a full professor position at the University of Breslau before finally finding a long-term post at the University of Zurich in 1921.
Wow. That kind of rapid institutional ladder climbing confirms his reputation was already solid.
Yeah.
He was a brilliant and highly sought-after theoretical mind right at the dawn of the quantum age.
No question about it.
So Schrödinger lands in Zurich. He's established, respected, but still intellectually rooted in the classical mechanics of his training. And it's here that he begins the, shall we say, reluctant process of engaging with the chaotic new ideas of the old quantum theory.
Ideas championed by figures like Planck, Bohr, and Sommerfeld. Yeah, he was definitely an intellectual latecomer to the quantum party.
And what was the state of that party at the time?
The scientific community was grappling with this fundamental disconnect between the success of classical physics on large scales and its spectacular failure on atomic scales. They had the ideas, quantized energy levels, wave-particle duality, but they lacked a unified, manageable mathematical framework.
And he absorbed these influences, especially after that rapid institutional movement in Germany. But the key breakthrough moment is really well documented.
Oh, it is. The year 1926 is one of the most important years in the history of science, and it's because of Schrödinger. He didn't just contribute to the discussion, he defined the language of quantum reality.
And the story goes that he was inspired by Louis de Broglie's hypothesis.
That's right. De Broglie had proposed that all matter exhibits wave-like properties. So Schrödinger asked the next logical question. If electrons are waves, what is the wave equation that governs them?
And he developed that wave equation, the one that redefined reality for us, while suffering from tuberculosis in a sanatorium in Arosa, Switzerland. It's an incredible testament to the power of a single mind during forced isolation.
It really speaks to the deep intellectual capacity that can thrive on isolation. He published the foundational paper introducing the time-independent equation in January 1926. It was titled Quantisierung als Eigenwertproblem.
Quantization as an eigenvalue problem. Let's break down the significance of that title for, our more informed listener. Why eigenvalue problem?
In simple terms, eigenvalues represent specific, discrete values that emerge as solutions to certain equations. For Schrödinger, the eigenvalues in his equation corresponded precisely to the discrete, quantized energy levels of the atom.
The exact levels that Bohr had proposed years earlier, but couldn't really explain from first principles.
Exactly.
Yeah.
Bohr had the right idea, but he lacked a rigorous fundamental equation to derive it. And the first paper's success was monumental because it demonstrated that this new wave mechanics produced the correct energy eigenvalues for a hydrogen-like atom. It was immediate, stunning verification that this framework was right.
But the output didn't stop there. The sources emphasized the breathtaking speed and cohesion of the following work. It was published in rapid succession. This wasn't just a single flash of insight. It was a complete conceptual overhaul delivered in 4 pillars.
It was an incredible run. The first paper laid out the time-independent equation, establishing the framework. The second paper followed just 4 weeks later.
4 weeks? That's unbelievable.
And the purpose of the second paper was to prove the comprehensiveness of the wave equation. He applied his new framework to classic physical problems. He solved the quantum harmonic oscillator, the rigid rotor, and the diatomic molecule.
So he was showing it wasn't a one-trick pony.
Precisely. The conclusion was undeniable. This equation was not a one-off tool for hydrogen. It was a fundamental law applicable across all sorts of quantum systems.
Now, the scientific landscape at that time was dominated by Werner Heisenberg's abstract, non-intuitive matrix mechanics.
Right. That method used tables of numbers matrices to describe observable quantities. And while it was mathematically sound, it was conceptually alienating for a lot of physicists.
It wasn't visualizable.
Not at all.
Yeah.
And so how did Schrödinger address this competition? That was the work of the third paper, published in May of that year.
And this was the unification.
This was the crucial act of unification. Schrödinger demonstrated the mathematical equivalence of his intuitive continuous wave mechanics approach to Heisenberg's discrete abstract matrix mechanics. There were two different paths, one based on waves, one on matrices, that led mathematically to the exact same physical answers.
So that cemented wave mechanics and matrix mechanics as two sides of the same coin. It consolidated the field and must have earned Schrödinger immense respect.
It was pivotal. But now we need to slow down a bit on the technical detail of the final paper because it reveals a critical mathematical elegance. The fourth paper addressed systems that change over time, the time-dependent Schrödinger equation.
Which is really the more powerful version.
It's perhaps the most powerful because it describes the dynamic evolution of the quantum state, how the wave function changes over time. That's essential for understanding things like transitions, scattering problems, and interactions. But mathematically, he ran into a wall of complexity.
How so?
Solving the wave equation for these dynamic systems naturally led to incredibly complex, higher-order differential equations. We're talking fourth and sixth-order equations, which are nearly impossible to manage analytically.
And the mathematical move he made to resolve this is what truly reveals the depth of his genius. He reduced all that chaos into manageable physics.
Precisely. To prevent those chaotic, complex, high-order solutions, he introduced a complex solution to the wave equation.
Meaning he used imaginary numbers.
He did. And this mathematical maneuver, involving imaginary numbers, immediately reduced the differential equation from the chaotic fourth or sixth order down to a single first-order differential equation.
Now, for the non-physicists listening, why was that mathematical move so revolutionary for the practical application of the equation?
Because it made the physics calculable. A first-order differential equation is the simplest kind. It's the quantum mechanical equivalent of Newton's F equals ma. By introducing complexity in the form of imaginary numbers into the solution, he achieved profound simplicity in the overall framework.
So this simplified, dynamic, time-dependent equation became the definitive starting point for all subsequent calculations in quantum physics and chemistry.
That's it. He didn't just write an equation, he developed a full, unified, and simplified framework for atomic theory in about 6 months. He fundamentally changed how we look at matter, and importantly, how we calculate its behavior.
And that framework was recognized 7 years later by the 1933 Nobel Prize in Physics, which he shared with Paul Dirac specifically for the discovery of new productive forms of atomic theory.
And yet, almost immediately after achieving that ultimate conformity, a Nobel Prize Schrödinger demonstrated that he was equally nonconformist in his professional and personal life, which led to rapid instability.
Let's track that instability. In 1927, he succeeded the great Max Planck at the University of Berlin. That's one of the most prestigious chairs in the world. But the rise of Nazism quickly made his position untenable.
He was ethically and morally opposed to the Nazi regime's anti-Semitism, and he was vocal about it. He left Germany in 1933, the very same year he won the Nobel Prize, and moved to Magdalen College, Oxford.
And that act of protest was a defining characteristic of the man. He was prioritizing principle over immense professional security.
He was. But his time at Oxford and his subsequent lecture invitation at Princeton in 1934 revealed the flip side of his nonconformity. His brilliance was undeniable, but his unconventional domestic life was a severe impediment to institutional acceptance in the 1930s.
Right, this is where it gets complicated.
This is the profound collision point. He lived with both his wife, Anne-Marie Bertel, or Annie, whom he married in 1920, and his mistress. Institutions like Oxford and Princeton were simply not prepared or willing to accommodate or ignore a ménage à trois.
And the sources indicate he was actually offered a permanent position at Princeton but declined.
Almost certainly because of this issue. He simply refused to compromise his personal arrangement for professional stability.
It's a remarkable portrait of a genius who felt comfortable defying social convention just as easily as he defied classical physics.
Absolutely. But speaking of defiance, despite inventing the fundamental tool of the quantum world, he was deeply fundamentally uncomfortable with the philosophical interpretation of what that tool suggested about reality.
This is the great paradox. He gave the world wave mechanics, but he detested the standard probability interpretation of quantum theory.
The Copenhagen interpretation, championed primarily by Niels Bohr and Werner Heisenberg. That interpretation suggested that reality only becomes definite, a particle or a wave when observed, and that until observation, particles exist in a superposition of all possible states.
And Schrödinger wanted an intuitive, continuous, deterministic reality, not a probabilistic, observer-dependent one.
He believed the theory was incomplete and deeply flawed in its interpretation. He continued to refer to his theory strictly as wave mechanics, resisting the shift to the generalized and philosophically challenging quantum mechanics. His dissatisfaction drove his most influential later work.
And the sources confirm he coined the term quantum entanglement in 1935 specifically to highlight the bizarre nature of the theory he created.
He absolutely did. Entanglement describes a connection between two or more quantum particles, such that their states are linked, regardless of the distance separating them. He called it the phenomenon that enforces its entire departure from classical lines of thought.
So for him, this non-locality, the instantaneous influence between distant particles, was a violation of common sense and classical causality.
He saw it not as a triumph of quantum theory, but as an indictment of its interpretational framework.
We even have that fantastic, fiery quote that captures his philosophical disdain for the way his beautiful wave theory was being used by the proponents of the Copenhagen school.
It reveals the purist and the aesthetician in him. He reportedly complained angrily to his students that, now the damn Göttingen physicists use my beautiful wave mechanics for calculating their shitty matrix elements.
Wow.
It's the rage of a physicist who believed in continuity and elegance, seeing his work co-opted for abstract statistical calculations that completely undermined his worldview.
And this entire philosophical war culminated in the most famous thought experiment in science, Schrödinger's cat. And we must remember the cat was never meant to be a serious proposal.
It was a conceptual weapon, a reductio ad absurdum. Proposed in 1935, following his correspondence with Albert Einstein regarding the famous EPR paradox, the cat experiment was specifically designed to ridicule the standard views of Bohr and Heisenberg regarding superposition.
He wanted to show that if superposition applied to microscopic particles, it must logically apply to macroscopic objects, and that the result was absurd.
Exactly. So let's walk through the setup for the listener. You have a box. Inside, there's the cat, a radioactive source, a Geiger counter, and a vial of poison. If the single quantum atom decays, the counter is triggered, the poison vial breaks, and the cat dies.
Straightforward enough. But here's the quantum twist.
Under the Copenhagen interpretation, before observation, the atom is in a superposition. It's both decayed and undecayed at the same time. Since the cat's fate is intrinsically linked to the atom's quantum state,
Then the cat, a macroscopic object, must also be in a superposition of states.
both dead and alive simultaneously.
And the moment the box is opened, the act of observation collapses the quantum state, forcing the cat to suddenly be definitively one or the other, alive or dead.
Schrödinger's point was simple. We know a cat cannot be simultaneously dead and alive. This literal macroscopic absurdity, a fuzzy, contradictory feline, must therefore expose the profound flaw or incompleteness in the Copenhagen interpretation when bridging the gap between the quantum and classical worlds.
It's just so powerful that the most common cultural shorthand for quantum mechanics is a critique designed by the very man who wrote the fundamental equation of the field.
And the 1930s were a period of immense political and professional instability for him. The philosophical nonconformity was matched by geographic instability driven by European politics.
After leaving Oxford, he took a position at the University of Graz in 1936, returning to his native Austria. He was likely seeking some stability after the Oxford and Princeton episodes.
But any sense of permanence was obliterated by the Anschluss in 1938.
The sudden, swift Nazi annexation of Austria.
Yes, and because of his established history, his outspoken opposition to Nazism, and his self-imposed flight from Germany in 1933, Schrödinger immediately became a person of interest and a target for the new regime in Graz. He was in genuine physical and professional danger.
The sources reveal this led him to a painful, desperate measure, issuing a recantation statement to appease the new authorities.
It was an agonizing conflict. He tried to comply with the new regime to protect his ability to work and live freely, signing a document expressing support. He later regretted this deeply, telling Einstein, "I wanted to remain free and could not do so without great duplicity."
And it didn't even work.
It didn't. Even this act of compromise failed to secure his safety. The University of Graz dismissed him anyway for political unreliability.
He suffered harassment and was instructed not to leave the country, yet he still managed a daring escape.
He fled to Italy with his wife, thanks to the help of others, before taking temporary visiting positions at Oxford and Ghent universities. This period of flight, moving between countries and institutions, lasted until 1940, when an extraordinary opportunity arose.
And that opportunity was Dublin, a surprising haven orchestrated by a head of state.
The Dublin years, from 1940 to 1955, were perhaps the longest period of sustained intellectual focus in his life, and they yielded some of his most influential, if non-quantum, work.
It all came from a personal invitation from Eamon de Valera, Ireland's Taoiseach.
Who was a scientist himself, trained in mathematics. De Valera was determined to establish a center of advanced research in Ireland. So he personally recruited one of the world's greatest scientific minds to anchor this new institution.
The Dublin Institute for Advanced Studies, or DIAS.
He joined DIAS as director of the School of Theoretical Physics, holding that post until he retired in 1955. He even became a naturalized Irish citizen in 1948, while retaining his Austrian citizenship. This period really underscores Ireland's commitment to supporting scientific excellence during a time of global war and instability.
I found the source material on his connection to Ireland quite fascinating. He wasn't Irish, yet he sought to root himself there through a surprising cultural belief.
It was an effort to integrate culturally. The sources note that in a 1940 interview with the Irish press, he spoke of the supposed Celtic heritage of Austrians.
Really?
Yeah, suggesting a deeper connection between us Austrians and the Celts, based, he argued, partly on linguistic evidence of Celtic place names in the Austrian Alps. It was perhaps a romanticized, personal way of claiming a spiritual and cultural connection to his adopted home.
And during these Dublin years, he produced a work that had nothing to do with solving the time-dependent wave equation, but whose influence reached far, far wider into the world of biology.
The book What is Life? Published in 1944.
This book is monumental, not for its physics, but for its audacity.
That's a great way to put it. Schrödinger applied a physicist's lens, specifically the laws of thermodynamics and statistical mechanics, to the most profound questions of genetics and life itself. The book addressed the crucial question, how can genetic material be stable, permanent, and yet small enough to reside within a cell, without being destroyed by the random thermal motion that characterizes all matter?
His argument revolved around the concept of order.
Yes, he introduced the concept of nogentropy, or negative entropy. Entropy is the measure of disorder, and the second law of thermodynamics states that disorder must always increase in a closed system.
But life seems to violate this law. It creates and maintains highly ordered structures.
So Schrödinger argued that living systems maintain order by constantly drawing orderliness from their environment, or feeding on nogentropy. They take in energy and excrete heat and waste, thus increasing the entropy of the universe around them while maintaining their own complexity.
But the truly revolutionary part was his proposal for the physical structure of the genetic code.
Right. He argued that for the genetic material to be stable and carry such a complex code, it couldn't be a simple molecule. It had to be in a periodic crystal, a complex, non-repeating chain molecule that was stable due to quantum mechanics, not classical thermal stability. This, a periodic crystal, he said, contained the full pattern of development.
And this seemingly theoretical proposal had an immediate practical impact. It links theoretical physics directly to the most famous biological discovery of the 20th century.
The sources confirm this essential historical detail. James G. Watson, in his memoir DNA, The Secret of Life, and Francis Crick, in What Mad Pursuit, both explicitly credited Schrödinger's book as a crucial, galvanizing inspiration for their work.
So the book gave them the intellectual confidence that they were looking for a complex, stable molecule.
The aperiodic crystal. And that molecule, discovered in 1953, was the DNA double helix structure.
It's powerful proof that sometimes breakthroughs in one field require the foundational thinking from a completely different domain.
Absolutely. But while inspiring biology, Schrödinger himself was still fighting his personal war against quantum randomness. He dedicated significant effort during the Dublin years to the pursuit of a unified field theory.
His dream was a theory that would unite gravity, electromagnetism, and the nuclear forces within the deterministic framework of Einstein's general relativity.
And he engaged in extensive, well-documented correspondence with Einstein on this topic. Both men were seeking a classical, deterministic, continuous field description. They were hoping to bypass the probabilistic and discontinuous nightmare that was mainstream quantum mechanics.
Two titans working together trying to put the genie of quantum uncertainty back in the bottle. Did he succeed?
Unfortunately, no. His final major attempt was his 1947 announcement, the affine field theory, presented at the Royal Irish Academy. This was met with a very lukewarm reception,
Even from Einstein.
especially from Einstein. He published a critique that called the results preliminary and inconclusive. The theory failed to lead to the desired unification. And the sources indicate that following this failure, Schrödinger essentially gave up his formal work on unification and reportedly never again collaborated with a major theoretical physicist.
So he failed to unite the forces, but did his attempt, or even his methodology, contribute anything foundational to the next generation of unification theorists?
Well, the significance of the failure is that it demonstrated the deep difficulty of marrying gravity with the quantum world, using a purely classical field theory, the approach both he and Einstein insisted upon. Their shared resistance to the reality of quantum mechanics led them down a path that ultimately proved fruitless for that generation.
So it's a dead end.
In a way,
Yeah.
but the rigor they applied and the problems they defined did help future theorists understand the vast gulf they were trying to bridge. Schrödinger has essentially confirmed that any successful unification would require accepting, rather than circumventing, the quantum nature of reality.
If the quantum world caused him profound scientific discomfort, his real intellectual refuge seemed to lie in pure philosophy.
That's where he could actively reconcile his scientific rejection of multiplicity with his spiritual craving for unity. He was influenced heavily by two giants of continental philosophy, Arthur Schopenhauer and Baruch Spinoza.
And his philosophical interests were not merely a hobby.
No, they were the backbone of his resistance to the quantum consensus. Schopenhauer in particular was the gateway. Schopenhauer argued that the world we perceive is merely representation or subjective interpretation, and behind that is the fundamental will or unified reality.
We see the direct echo of this influence in his later lectures. The sources reference his 1956 lecture, Mind and Matter, which contains a strikingly Schopenhauerian line.
He stated that the world extended in space and time is but our representation. This is almost a direct restatement of the opening sentiment of Schopenhauer's main philosophical work, the world as will and representation. For Schrödinger, science was powerful, but it could only ever describe the representation, the external manifestation, not the underlying will or consciousness that perceives it.
But his philosophical engagement went far further than European thought. It extended deeply into Eastern religion and the ancient philosophies of India.
Yes. Schopenhauer's work was the key conduit that introduced Schrödinger to Indian philosophy, specifically the Upanishads and the non-dualist school of Advaita Vedanta. This is where the narrative thread of rejecting multiplicity becomes absolutely explicit.
And even though he was an atheist, the sources note his strong interest in Eastern religions and pantheism. It seems he viewed his scientific work itself as an intellectual approach to divinity.
He absolutely did. The core tenet of Advaita Vedanta is the concept of Brahman, the ultimate reality, and Atman, the individual soul, being fundamentally the same. The whole idea is tat tvamasi, that art thou.
The ultimate rejection of duality and multiplicity.
And Schrödinger embraced this, using religious symbolism even while remaining skeptical of organized religion. And he arrived at an astonishing conclusion about consciousness, drawn from this synthesis of physics and Eastern philosophy, which perfectly mirrors his scientific resistance to wave function collapse.
It's the ultimate synthesis for him.
It is. He embraced the idea of the unification of minds or consciousnesses. He argued that the apparent multiplicity of individual minds, you and me, as separate entities, is only an illusion arising from our perception of time and space. He stated unequivocally, "In truth, there is only one mind. This is the doctrine of the Upanishads."
So he was proposing that the singular you experiencing reality is merely a temporary manifestation of a universal, unified consciousness. Why did he feel compelled to argue this from a scientific perspective?
Because of the observer problem in quantum mechanics. If observation is necessary to collapse a wave function, where does the collapse occur? does a collapse in the cat's eye, in the physicist's brain.
Mm.
He saw a deep logical impasse. He believed the only way out was to assume that consciousness itself cannot be a physical product of the brain.
And he said that directly.
He explicitly stated that consciousness is absolutely fundamental and cannot be accounted for in physical terms. For consciousness is absolutely fundamental. It cannot be accounted for in terms of anything else.
That is a staggering statement from one of the fathers of modern physics, a declaration that consciousness transcends the very physics he helped create.
It's the key takeaway about his intellectual life. His entire career was dedicated to finding unity and continuity, whether it was unifying fields, unifying physics and biology, or unifying consciousness.
And his later years were marked by this philosophical emphasis and further resistance to the mainstream scientific consensus. When he returned to Vienna in 1956, he refused to speak on nuclear power.
Due to his skepticism about its implications.
Right. And instead, he gave a purely philosophical lecture, doubling down on his non-materialist worldview.
And he continued his resistance to standard quantum theory, turning firmly against the concept of wave-particle duality, the idea that quantum entities can behave sometimes like waves and sometimes like particles. He promoted the wave idea alone, seeking a continuous, fluid description of reality rather than the discontinuous probabilistic jumps required by the particle interpretation.
He was always searching for a reality that felt more intuitive.
Always. In fact, in 1952, he published work that retrospectively anticipated one of the most radical alternative interpretations of quantum mechanics, the many-worlds interpretation.
How so?
He suggested that the different terms of a superposition evolving under his equation are not alternatives, but all really happen simultaneously.
So instead of the observer collapsing the wave function, Schrödinger essentially suggested that the universe splits, meaning the dead cat and the alive cat are both real, just existing in different simultaneous universes.
Which helps resolve the observer problem by saying everything possible happens, a far cry from the single definite reality proposed by Copenhagen.
As we transition, we must address the difficult truth that Schrödinger's professional brilliance and philosophical depth contrast sharply with the documented complexities and controversies of his personal life,
Which repeatedly caused professional instability, and now necessitates a profound reappraisal of his legacy.
We have to adhere strictly to the factual reporting provided in the sources and biographies here. He married Anne-Marie Bertel, or Annie, in 1920, and their marriage was unconventional from the outset.
The menage a trois arrangement became highly visible and professionally damaging during his time at Oxford and Princeton. When he fled to Dublin in 1939, this arrangement continued.
He obtained visas for himself, his wife, and another woman.
Hilda March, who was the wife of an Austrian colleague, Arthur March. Schrödinger had fathered a daughter with Hilda in 1934, and the Taisich, Emon de Valera, personally secured a visa for March to live with them in Dublin. This domestic arrangement was acknowledged, if not accepted, by the highest levels of Irish government.
This arrangement, however, only scratches the surface of the deeply concerning details regarding his relationships. Biographers have reported serious and disturbing information about his predilection for young women.
Indeed. The primary source for many of these details is the authoritative 1989 biography by Walter Moore. Moore described Schrödinger as having what he termed a Lolita complex and a predilection for teenage girls. This is a profoundly difficult and sensitive topic, and we have to report the documented facts impartially as they appear in the sources.
The sources specifically detail a relationship that began around 1926. Schrödinger was 39, and he was tutoring a girl named Ithy Younger, who was 14 at the time.
Moore relates that the tutoring relationship escalated, including a fair amount of petting and cuddling, and that Schrödinger became infatuated with his pupil. The relationship became sexual not long after her 17th birthday.
And later, in 1932, when she was 20, she became pregnant.
That's right. While Schrödinger offered to take care of the child, he refused to divorce his wife, Annie, which led Ithy to arrange for an abortion.
This pattern was apparently consistent throughout his life and was rooted in a problematic worldview regarding women.
Biographer Walter Moore explicitly stated that Schrödinger's attitude toward women was that of a male supremacist. The sources note that he also utilized his own diary entries, where he expressed attraction to women who were as nearly connected to the preferred springs of nature as men of strong, genuine intellectuality.
And this behavior continued through his time in Ireland, where he was supposedly seeking intellectual peace.
Yes. The source material, including articles from Der Standard, states that while in Ireland, he fathered children from two other women, one described as a 26-year-old and the other a married political activist. However, Moore's biography clarifies that neither of these women were his students.
But there was another incident.
Yes. Moore's account also described a deeply troubling episode in Ireland where Schrödinger was infatuated with a 12-year-old girl named Barbara McEntee. He reportedly only stopped pursuing the relationship after receiving a serious word from a concerned third party, but later listed her among the unrequited loves of his life.
These facts, documented in his own papers and detailed by biographers, has led to a significant institutional reconsideration of his legacy, particularly where he spent those years in Dublin.
Absolutely. The tension between his genius and his actions reached a critical point. In January 2022, Trinity College Dublin, where he gave highly influential lectures, announced a tangible and necessary response.
They renamed a lecture theater.
A lecture theater that had borne his name since the 1990s was formally renamed to the generic Physics Lecture Theater, and his portrait was removed.
That action speaks volumes. It wasn't taken lightly, and it was explicitly linked back to the sources we've discussed.
PCD released a statement acknowledging the indisputable scientific contribution of Erwin Schrödinger, while acknowledging disturbing information, much of it from Schrödinger's own diaries, which is now also known. It shows that institutions are actively grappling with the complexity of separating or perhaps acknowledging the fusion of scientific genius and documented personal misconduct.
It's a powerful moment of reappraisal.
It is. Schrödinger died, fittingly, in his native Vienna on 4 January 1961 at the age of 73 of tuberculosis. And even his burial involved a final, curious contradiction.
He was a lifelong atheist.
Yet he was buried in a Catholic cemetery in Altbach. The sources indicate the local priest allowed the burial only after learning that Schrödinger was a member of the Pontifical Academy of Sciences, a position he had held since 1936.
So, despite the necessary and painful reevaluation of his personal life, his intellectual contributions remain colossal and fundamentally undeniable. They reshaped our understanding of the physical world forever.
Without question. At the most technical level, the Schrödinger equation remains his most enduring legacy. It is the definitive equation of wave mechanics, used daily across physics, chemistry, materials science,
Engineering disciplines.
to predict molecular behavior and quantum phenomena. It is the cornerstone of modern science.
And for the general public, the philosophical weight of his ideas persists through popular science, even if the general understanding of his most famous experiment is divorced from its original critical intent.
That's where Schrödinger's cat comes in. The thought experiment designed to illustrate absurdity remains his most enduring popular legacy because it perfectly encapsulates the strange, counterintuitive nature of the quantum classical boundary. He forced science to confront the limits of interpretation. He is justly recognized as one of several individuals called the father of quantum mechanics.
And the physical commemorations of his monumental impacts span the globe and even the solar system.
They certainly do. He has a crater named after him, the Schrödinger crater on the far side of the moon. Closer to Earth, the Erwin Schrödinger International Institute for Mathematical Physics was founded in Vienna in 1992.
And his face was on money.
For years, his likeness was prominent on the 1983-97 Austrian 1,000 shilling banknote. Buildings are named in his honor at the University of Limerick in Ireland and the Erwin Schrödinger Zentrum in Berlin. Even CERN, the home of particle physics, has a root Schrödinger.
And a Google Doodle, of course.
His 126th birthday in 2013 was celebrated with a Google Doodle, recognizing his profound influence.
So as we conclude this deep dive, what does this synthesis of the sources tell us about Erwin Schrödinger? We have explored the man who created the definitive equation of wave mechanics, coined the concept of quantum entanglement, and wrote the book that inspired the discovery of DNA structure.
And he was an uncompromising intellect who sought unity, continuity, and deterministic elegance across every field he touched. I think it tells us that genius is defined by paradox. His intellectual stature is immense. His ability to synthesize classical physics, quantum theory, biology, and philosophy is unparalleled.
And this is directly contrasted by a fierce nonconformity.
A nonconformity that drove both his courage-fleeing Nazism and his documented personal flaws, which ultimately required his legacy to be physically revised in institutions like Trinity College Dublin. He was a rebel who rejected atomization in physics, philosophy, and domestic life, and that drive resulted in both his greatest triumphs and the most painful aspects of his history.
So what does this all mean for us, the learner, as we try to integrate this complex reality? Here's where it gets really interesting.
We discussed Schrödinger's ultimate conclusion, drawn from his reading of the Upanishads, that the apparent multiplicity of our individual consciousnesses is an illusion.
That, in truth, there is only one mind.
Right, so if this towering figure, who understood the mechanics of matter better than almost anyone, ultimately believed that all individual perception is fundamentally unified and continuous, what does that mean for the unique, solitary reality you perceive every day?
It provides a final, provocative thought. When you face paradoxes, whether the scientific paradox of the quantum world or the everyday contradictions of life itself, consider the possibility that the boundaries you perceive between yourself and the universe, or between your consciousness and others, might be a fundamental illusion.
If Schrödinger sought continuity in the quantum wave function, perhaps we should seek continuity in our own experience, recognizing that the one mind he described is the only thing that can make sense of a half-dead cat.
Something for you to explore on your own.